Hi, I'm staying in the Winter Festival mood and taking a second look at my Robot Santa project. Last time I looked at the mechanicals and hardware design. This time I'm going to look at the software. Robot Santa uses the Robot operating system for control. This provides communication between the Raspberry Pi, which handles high-level functions like the facial detection and processing, and the Pico, which handles the servos and LED control. We need to look at two parts. First, the firmware, and I'm using Micro ROS there, and it's written in C++ for the Pico. Then on the Raspberry Pi, I've got OpenCV and Python code detecting a face and instructing the robot to turn towards my face. Please do like the video and subscribe. I do appreciate it.
This video is sponsored by Cancun. Cancun is a friendly retailer in the UK for modules, components and electrical equipment. Cancun has kindly offered a discount to my channel viewers on the first order. Just quote Dr. John EA20 at checkout to get a 20% discount. This excludes electrical test equipment and tools. If you're in the UK, go and check out Cancun today. Make sure you check out the part 1 video on Robot Santa, because that's where I talk about the mechanics and the electronics that actually work the head. Here we're just going to go straight into the code. All of the code for this project is shared on GitHub. So over in VS Code I've got my Robot Santa repo. Let's have a quick look at the libraries I'm using here. I think first is probably a good place to start. We are of course using Micro ROS. The firmware is all written to use Micro ROS to talk out to the ROS ecosystem. I'm using FreeRTOS kernel because I want to be able to multitask. I want to be able to instruct the servos and indeed the LEDs to go and do something while I keep looking for new messages and answering queries. And I'm using the IGEN library. I'm not entirely sure how you pronounce that. That library gives me some of the calculations, so I need to go from Euler to quaternion notation for rotations for this, and therefore I'm using that library to do that conversion. Nothing really very sinister in that. So the code itself, let's have a look and start in main, because main is always where everything starts. So our main task and the launch of our main task here, it really just boots everything up. So we're setting up head, which is strangely the actual head. It's got the pan and tilt control servos. So for our pitch, we're using the GPIO pin 22. For yaw, I'm using GPIO 21. The eyes have 3 colours associated with them. They're also on GPIO pins, though they're on pads 2, 3 and 4. And I'm going to start by setting the colour to red. So we come up and eyes go red. Head entities is really important. Head entities is where most of the code is that converts our world of ROS and handling those messages over into the actual instructions for our head and eyes. Head and eyes are basically just there to actually go and do stuff. And the head entities is what we give to our Micro ROS bridge, and the Micro ROS bridge then goes off and does the communication stuff for us. So this is very similar to stuff where I've done with DDD or with that video turntable I did quite some time ago on Micro ROS. Go and check out those videos if you want to know more about this sort of stuff. Let's have a look at head. So the head is really just about having 2 servos within it. So if we look down here, look, there are 2 servos. And it is a task that is going to continue to run and it can get an instruction to move to a particular radians position in terms of pitch and yaw in a number of ticks. That's important because I want my movements to look natural, so they are all going to take a particular amount of time to move, and as they move they're actually going to accelerate and then decelerate. And I'm using some little tricks in heads to do that, and I talked about this in the Halloween episode because I'm using exactly the same technique here of basically using a sine wave to accelerate and decelerate. So when I actually do the move rad, you'll see here I actually pre-calculate the offset in terms of from that sine wave in order to work out actually how much of the movement I'm going to do at every interval of that time. And then within run we're actually executing that. So we're taking where are we trying to go, and we're going through and working out which bit of it and doing incremental pieces to accelerate and then decelerate. And head uses servo, and I've got servo classes, and I've done videos on servos before, and this is really just setting up our servos and our GPI pin to be able to provide the 20 millisecond pulse widths required for these servos, and then being able to actually set that pulse width based on the number of radians and radian position. So and radians goes between 0, which is the center position, and then plus and minus pi over 2. So that's servos. How about the eyes? Well, again, we've got similar structure in eyes. We've got the eye agent, which basically just contains 2 eyes. If I look down here, well, actually it contains one eye or one set of eyes, because the eyes are actually connected to the same cables and that same GPIO ports. So we set them up, giving it the red, green and blue GPIO pins, and then we set a color. And all of the set color is doing is it's actually it's also instructing that we are going to move through that color over a period of time. And so there is a little fast rotation movement of color, so that we slowly go from whatever we were before to our new color, an increment at a time at a 10 tick cycle. There's a delay of 10 ticks down there. The actual control of the GPIO pads is done in eyes, and that's basically just setting up, sorry, wrong file there. That's just setting up our GPIO pads and then calculating what is the level between 0 and normally 16 bits, so 0 L X FFF to get that. Now there is a problem, and I talked about that on the last video, that I've accidentally clashed slicers. So the blue channel actually is counting only between 0 and 20,000 rather than FFFF. Yeah, so I had to be a little bit clever in the maths in here to get that to work, so that we get proper colours across all the colours of the RGB. So those are all really straightforward. The other bit of code in here is really what is going on in head entities, and this is really about managing the messages coming through from our Micro ROS, or through Micro ROS and from the ROS ecosystem. So if you remember, there are 2 messages. We are going to get a pose message to move, and we're going to get a color message about doing the eyes and setting the eyes color. Let's talk about the pose message first. And if you remember, a pose message basically has a criterion of the angles that we wish to rotate to in terms of pitch, roll and yaw. Now we can't roll, so it's only actually pitch and yaw. that we're actually worried about and interested in. And so if I start having a look through head entities, which is where really everything is, so we are setting up our subscription to post messages here, and we take a post stamp message, and when that on the channel, do pose. To do that, I will actually have to set up here we go, an executor to take that message and to be able to handle that. And I have to tell Micro ROS I've got an executor and that I've got enough channels for that. One of the slight bugs I made in this when I was coding it is I unfortunately was telling my code that I'd only got a single executor, and I got two. And I was wondering, well, why does only one of them work? Well, only one of them works because you've only told it it's got one. It hasn't got enough for the two you've tried to add. So we have two executors here, but we got this pose one. And that is giving us information through our callback mechanism. So in our handle subscriptions, we can either get a pose context or we can get a eyes context for the eyes message. So with pose context, we can, here we go, pose. We basically are going to get this quadrant position, and I need to get that into a standard Julia format, so I can basically just extract out what is actually the pitch and the yaw. I print them out because I had some problems when I was working through this with just getting everything to work properly, and make sure that actually I am getting the pitch, roll and yaw I was expecting. Things were flipping. One of the reasons is that if you try to drive pitch in quaternion beyond minus or plus pi, then you can get some very strange behavior, and you start getting the entire thing flipping, and roll suddenly becomes 180 degrees out. So to avoid those problems, we just stay between minus pi over 2 and plus pi over 2. Which, to be honest, is fine because our server can only turn 180 degrees. So 0 or pi. So from 0 to pi over 2 and 0 to minus pi over 2, that's fine, that's within that range. I also need to do a bit of calculation around time here, because I use a trick here that I take the timestamp that's coming in on that pose stamp message and I calculate how far in that is into the future. Because in ROS2 you've got a nice clocked ecosystem. So we've got a common clock, and I can therefore predict how much time and when I should get to this new location, and that's how we're getting that time, and then calculating that, and then calculating what that means in terms of ticks for FreeRTOS. So that then gives us enough to actually tell our head to move to a pitch, yaw and ticks. Job done. So eyes are actually even easier. So again, we are creating a subscriber for eyes that is going to sit on do eyes, and it's of type color RGBA. Now color RGBA is really just 4 float values. Red, green, blue, and A I think is ambience. I didn't use the A. So again, we need to set up a set of we need to set up an executor for this and add that in. And then within our handle subscription, if the context is our eyes, we're going to run off and actually process handle our eye message. And The easy thing here is actually for eyes we just need to convert what is a float between 0 and 1 into a value between 0 and 255. So an integer 8-bit value, unsigned obviously, and then we send that off to our eyes to change the colour. Simple. So that's it. This is a really very simple. And from this, we get the ability to now be able to instruct our head to move and instruct our head to change its eye colour. So using the ROS2 Topics Publish utility, I can publish a colour for instruction for our eyes and switch the eyes to be green, and then let's make them go red. There we go, and finally let's try white. In Python I've got this script pose, which is basically just sending a pose message to our head. Now the reason I had to do that in Python is so that I can manipulate the timestamp. If I can push that through the ROS2 Topic Pub utility, I can do that, but the timestamp will always be now. And actually I wanted the timestamp to be now plus a duration in seconds. And that's basically what this is doing. So it just takes our yaw and pitch, and it converts those into a quaternion so that we can send it within this pose stamp message. Remember, this is a quaternion structure in this particular message type, so I need to be good and convert to that. Converting it to that, I did some checks, so I'm just back converting as well. Don't worry about that too much. And then I just publish it. It's very easy to do this stuff in Python, and it's a nice little utility here just to tell the head to move to a particular rotation. So using this Python pose command, we can instruct the center to turn to the left, to turn to the right, -1, and to turn back to center. So that gives us yaw. Now we can do the same with pitch, of course. So it hasn't got quite as much pitch movement, but we can get them to nod forward there and to nod back, and they straighten up a little bit. Face pattern in Python is doing the real work. It's doing the face recognition and then instructing the movement of our head, and indeed the changing of colour of the eyes. And really all this face recognition is done using CV2 as a library. So I've got a pose node here which has got a whole load of stuff in it. I'm just going to take you through a few of the highlights here. So really from a facial recognition point of view, all we are doing is that in this function here. And we are capturing an image from using CV2. We are then putting that into grayscale. We're then using a detection, multi-scale detector, and that's set up to use, it goes up here, the HAR cascade frontal face defaults. That's a nice standard, comes out of the box, so that will detect faces, and it gives us a set of faces. All I'm going to do is say that I'm actually interested in where the first one is. If we're done with a set of face, we don't find it, we return. But that's all it's doing, is finding that out, and then we're working out what is the yaw and pitch as a delta from our current position for the center of that face. And I can do that by knowing what the actual width in terms of radians and height in terms of radians our camera is. And some of that was stuff that I took from the spec of the camera, and some of it's stuff that I experimented a bit to find out. There is a little bit to think about, because if you look at our model, where is that camera on our model? Is it actually straight on the pivot point? No, because I pulled it forward and up to the top of the chin, and because of that there is a little bit of difference, particularly from a pitch point of view. I found in the angles, so I fudged this just a little bit. So published pose is exactly what we've seen in terms of the pose Python before. Nothing can change there. And then our really publishing eyes is very similar to publishing a pose. A nice simple message published from Python. So the only other thing in really here is our go loop, which is just the continuous loop of continuously asking it to do facial detection and then taking action from it. So if we've detected a face, then we make sure our eyes are green and we move towards that face. If we've not detected a face and we don't detect the face for a period of time, then I've actually instructed the head to go into a bit of a what did I call it? I called it a patrol. So it goes into a patrol and it goes through a set of angles in patrol mode, in the hope that at some point in that it picks up a face and can go back into face recognition mode. When in the patrol mode, the eyes are blue. That's it, really. It's yeah, it was it's not the best written Python in the world, I must admit, but it does the job, and it was quite fun and quite easy to get running. In this video I'm going to show the facial detection. You can see that the eyes go green as I'm detected, and you can see both the wide shot of the head turning around and following me, and some really dodgy hand camera work there, trying to give you a sort of eyes perspective of what I'm saying.
I found the coding for this project very straightforward. Following a few examples online, it was quick and easy to get OpenCV to detect faces. The math was fairly easy to work through too. Of course I had a few failures, like forgetting that the camera is moving and the servos are not. So the angle I'm instructing the servos needed to be a delta that's moving around. Oh well. I hope you enjoyed the video though. Thank you very much for watching. Please like the video as it helps others find it, and please subscribe and hit that notification button so you don't miss that next video. Goodbye for now.